want to talk a little bit about notional machines, and and basically then do a whole diversion on a very related topic in Lambda calculus. So I'm working in the Lucha research group with Matthias Hauswit, Andrea Galdabino, and Luca Chiodini. And we're also collaborating with Johan Juring from Utrecht. So before we get started, though, I'm going to ask you to fill this poll. Let's see if this is going to turn out to be a good idea or not. I'm going to put this link here in the it's tinyurl.com/lambda-poll. So here's the chat. Bam. That is it. So my ambition is that it could adjust a little bit the talk, right? So it's these three questions. How familiar are you with the Lambda calculus? And it's from 0 to 3. If you are familiar with at least two of these terms, essentially call by value, call by reference, or anything like that. It's very lenient. If, any of these two, any two of these, or at least two of these. And if you are familiar with the Y combinator, if you could sort of walk through an example. And I'm looking at the clock. You have 1 minute. Actually, I can already start to look in the answers here. You can increase the font size here. So let me see, where are we? Okay. I should have made a bet, before. Should have made a bet on this. Okay. Okay. I think that's already gave me the gist. Okay. Let's see. All right. Let's go because we're gonna have time. So let's do this. So programming is hard, right? So several research studies in computer science education have shown this. You've probably seen Matthias's talk about the rainfall problem, detailing this. If programming is hard, what can we do about it? Right? And probably you may have resorted to notional machines while you're teaching, even without knowing, right? And what are then notional machines? Well, if you ever use, for example, to if reason about the state of memory during program execution, or if you use a control flow graph to explain control flow, right? Or even analogies such as a variable is a box that stores a value, etc. Or maybe a variable is like a parking space because it has types, and so you can't park any car in any parking space, something like this. All of these are then examples of notional machines. So a notional machine is a pedagogic some aspect of programs or programming, right? This is a definition that came out of this group that has been working on notional machines, and they collected these examples, the ones that I showed, and many more from actual teaching. But really, the question then is that a given notional machine is correct, right? Meaning that if you're using it to represent a certain aspect of a program, well, how do you know it's actually representing the thing that you want to represent, right? So the situation is that you have some programming language L, more specifically probably an aspect of this language that you're focusing on, right? And then you have some notional machine X, right? And you want to sort of have some kind of correctness argument there, right? So I'm making up this symbol, funny symbol here, like a tilde with a question mark, something like there's a kind of relationship between them, right? But for you you need to really know what exactly is this aspect of this programming language that you're talking about. By the way, what is this other thing, right, that you're using as an analogy? I mean, if you or a diagram or something, if you really want to nail, sort of be more precise, to be much more precise, right? So and if you're talking about the thing in the left, right, then you're in luck, right? Because for programming languages, there are plenty of those. And in fact, this is what actually I want to talk then about in this it's basically a whole parenthesis. I'm going to open a parenthesis here and talk about the Lambda calculus. Now, you're probably familiar with Lambda as a language feature, right? So if you look at the TIOP index, the languages that show there on top, all of these have Lambda. So you probably used it while programming, right? But really, what I want to try to argue is that Lambda calculus is far more than just a language feature, like let's say a for loop, right? So what is the historical context, right? So here in the left, you have a picture of 1935, and in the right you have a picture of Alan Turing 1936. But no, hold on, wait a minute. No, sorry, that was the wrong picture. That's the that's the right picture. Got confused there. Alan Turing 19. This is the historical context. Well, the historical context is that following the work of Hilbert in trying to essentially prove the entirety of mathematics, with logic, and then the subsequent Gödel incompleteness theorem, right, that demonstrates that then this is not possible in the first place, that any system, let's say, as complex as arithmetic has statements that are true but aren't provable within the system, right? Then, so if there are things that aren't decidable, things that aren't provable, what is this, right? How can I sort of have some kind of language that describes this? These are two essentially, these are two approaches to try to tackle this problem. And in fact, Turing was working concurrently, and it has a comparison between his work and the work of the Lambda calculus and sort of which is known as the Church-Turing thesis. And so this is the historical context then. And but what is finally the Lambda? Show me, what are you talking about? Well, so it's a programming language, even though it wasn't invented, it was even before there were computers, but it is literally a programming language, and a programming language has a syntax and a semantics, right? And so what is the syntax? Well, the syntax, very simple. There are only three constructs, right? A term is either a variable or a abstraction. It's lambda x, where x is a variable, dot, and then another term, right? This would be, let's say, the body of your function. So this is like an anonymous function, or then application in which you apply a term to another term, right? You apply a function, and the semantics only one computation rule, right? A rule that actually computes something. There's only, which is this one. If you have an application that in the left you have a function, so if you're applying a lambda term to another term, this reduces to, right? So this evaluates to well, one step of computation, right, is that you only get you basically get the body of the function where every occurrence of x, which was the argument, is then replaced by t2, right? So in the body of this term, you can imagine this term could be a whole whole thing, big, right? So this is it. And there's no prescription even of an evaluation strategy, right? So it doesn't say which term is going to be evaluated when, etc. The syntax has three constructs: a variable, a anonymous function, essentially, which is called the lambda abstraction, right? With one argument, the argument is x, and here's the body, right? And then application, right? And that you compute. Whoops, my bad. You compute by essentially applying a function to term, right? Applying a lambda abstraction to a term, and the result of this is the body of the function where all the argument is replaced by where the parameter, right? So the formal parameter is replaced by the argument that you're passing in here. Okay, now. Okay, and then I said there are two conventions, right? So application is left associative. So if you write A, B, C, and D, it's applying to the left here, and the body of a lambda extends as far as possible to the right. So this is not, lambda x A applied to B, but the parentheses include, so the application is inside the body, right? Not the lambda. Okay. Now, what about multiple arguments? I mean, how far can you get with this thing? How can this be Turing complete? Well, no problem. Let's see. I even wrote here an example in JavaScript, right? So let's say that you have a function of 2 arguments that discards the second argument, for example, right? You can just rewrite this as then a function of 1 argument each, right? The first function returns another function which then consumes the second argument and returns the argument of the first function, which then would correspond then to this term here, right? And now let's see. Let's do an example, right? Let's run this. So let's say that this term is here, and then you're applying it to A and B. I'm going to just put a little bit of spaces here so that I can put the parentheses in case so that you don't get lost, right? So this is the body of the lambda t here, and this is an application. You first apply to A, right? And so this leads to the body substituting t by A, right? So that's what you get here. And then when you apply this to B, well, you're not using F anywhere, so that's just the A. Right, so you essentially did what the example in JavaScript was, right? So you selected the first term. So it's essentially even though you used only functions with 1 argument, you actually effectively have a function of 2 arguments. Right? Okay. So sure enough, but then where's the data, right? Where's the data? I mean, you have data, computation, and data, but do you, right? I mean. Computation, data, right? So we know that we can encode computation as data, right? And you store it, for example, or it's in memory. And you can also represent data as computation, right? So for example, we're going to see this example here with booleans, right? So the goal is that you want to write some kind of function, let's call it if-else, that when applied to some term that represents a Boolean is going to select either the first or the next or the other, second argument, depending on what this term here is, right? And so here it is. So actually, this very term that we used before represents true, right? Selecting the first out of 2 things represents true, and selecting the second would be false. And if else, then would be simply something that takes one of these as a first argument and then applies it to the next 2 things, right? So here, for example, an if else applied to true should give you X, right? And if you follow here the steps, if else is this guy. So this equality here is this is basically I'm just using, this is like equal in math. Okay, so it's not an assignment. This is it's just let's say a shortcut so that I don't have to write the whole thing really ugly here, right? So here if else is this guy, and so you replace then the body is this, replace B in the body by true, and you consume the other one. X comes in here, and then X, and then true, then selects the first one, right? I mean, I can, in the end, if there's some time left and you want, we can sort of look at this more slowly. And what about numbers? Well, numbers. Easy. You use, easy. Yeah, you use piano arithmetic, right? In which a function application then represents, adding 1 essentially, right? And what about compound data pairs, for example? Well, you can use the same idea of booleans to select terms, right, out of it. And then you keep going. But then, of course, what about recursion? I mean, if you don't have a top-level name, how can you write anything that is recursive, right, with that thing? And so, here it is. So, you can, for example, write what is called an omega, right? That is sort of essentially the simplest thing that can repeat, which is here, this term, when you apply it here, right? So you're going to get x applied to x, where x was actually substituted by this, right? So you're actually going to get the very thing that you started with. And so therefore you do the next step of computation and you get back to where you were, and so on, right? So this thing is going to it's going to infinite loop, right? It's going to diverge. And so you essentially use this idea to encode what is called the fixed point combinator, or the Y combinator, right? Or in this specific case, this is the call by value Y combinator, right? Which is very intricate. It sounds like, so I'm definitely not going to walk through it here. But notice that it has this, repeated form to it, and there's like it's kind of like a double self-referential thingy here, right? If you dig into it, and the idea is that you can write factorial, for example, by applying this term to this function which actually computes the factorial, right? So it is true that you don't have a top-level name, but you do have names in the arguments, right? So here it is. If you want to write your factorial function and you want to refer to factorial here, this can't be a top-level name, but it can be something that was passed to you, right? And so this essentially it factors out the essence of recursion into another function, which then can turn any other function into a recursive function, essentially. And the final thing then that I want to, the final thing, okay, I was supposed to say the final thing in 2 slides from now. But the last thing that I want to point out here quickly, this is really, I could not say that, this is what I think is the most unbelievable result that nobody knows about, kind of. I mean, maybe everybody knows about. I should have asked that in the quiz, actually. So, which is this propositions as types, also known as the Curry-Howard correspondence, Curry-Howard isomorphism, right? Which is that if you add types to the lambda calculus, to this thing, then simply type lambda calculus, right? So this corresponds to first order logic, and in fact, you can, there is a correspondence between all sorts of many kinds of logic, right? So developments in logic and in type systems. So essentially, there is something really, much more fundamental with types and lambda calculus than sort of meets the eye, and so there's this paper here in the communications of the ACM, in which Phil Butler essentially sort of goes through the history of this and how this is really it's at the heart of proof assistance and all sorts of developments in mathematics. So and computer science, obviously, and the sort of moving towards unifying many of these things. And so essentially the takeaway here is that the lambda calculus is a Turing-complete language. It is used to reason and write proofs about programs and programming languages. Lambda and types are as foundational as logic, essentially, and we're trying to use that and other tools to reason about notional machines. And on a lighter note here, Simon Peyton Jones in the History of Programming Languages, he was talking about Haskell, etc. And he said, well, we were too young for the 1960s, so we had missed the all you need is love, but we had a slightly more geeky slogan, all you need is Lambda. So I thought that was so, so funny in a silly way, funny, etc. So that's where the thing in the abstract comes from. I also have a bunch of references here that may be useful if you're interested. Nice, thank you.